First, so we talked very briefly, kind of as we were leaving, about some of the mid-semester evaluation feedback I got from y'all last time, but I wanted to talk a little bit about this was the answer that I had the most concerns about reading it. This shows that a whole quarter of you, so it's how often are you confused about what homework problems are asking, even after thinking it through and looking over the example problems in the book. And I got a whole quarter of you say very often, and a half say somewhat often, and that is more than I want. That, I think, indicates some breakdown somewhere. And so what I did, after seeing that, is I looked through the next homework assignment, and then I also looked through this lecture, and I tried to tweak both of them a little to make sure that you have the tools you will need for your homework going in. Now, that doesn't mean you won't need to look at the book for things we don't cover, things like that. Just tried to streamline it a little bit. And I was wondering about your thoughts on this. If anyone wants to share about why, if they have any ideas of why they have a hard time understanding what some of the homework problems are asking. Okay. All right. If you would like, if you have ideas, you just don't want to say them out loud, tell me about it later, or just email me. This is one of the skills we're trying to teach you, is how to sort of take the problem as it is stated in words and sort of figure out what you're supposed to be doing. That's, as I said, that's a skill we're trying to teach you. And so if you're not learning that, I want to adjust to make sure that happens. So also about the homework, we are much more caught up on grading than we were, but we aren't quite there yet. But hopefully, we are going at a pace where we will have everything graded before the next exam. The next exam, by the way, is we have this class today. We have a class on Thursday and one on Tuesday, and then it's the next midterm. Okay? Yay. Then we're going to have another class sort of discussing the project, and we'll be mostly working on the project until near the end. I will try to get the project proposals graded as quickly as possible, because first of all, you need permission to start working. I've told you before, and also I want you to have my comments when you do start working. I'm not going to promise an exact date I'll have it done by, because you always run the risk of just disappointment for everyone when you do that. But I'm going to work on getting it done as quickly as I can. Okay, so last time we talked was a whole week ago, which is a long time in retaining brand new information time. So I wanted us to do a couple of review questions, and we're going to do chat with your neighbor for these. So remember, these are the 3 different mechanisms of heat transfer we discussed. So I want you to chat with your neighbor and explain the difference between these 3 things.
Hi neighbor, I'm learning. Convection, and radiation. Radiation is something that gives off light. Convection is just moving fluid. Conduction is just things that are
think that their neighbor explained this particularly well. Oh, okay. All right, could you explain to us the difference? Yeah. I actually really like that. So what she did, so everyone can see, is she said conduction, convection, and then radiation. Is that it? What was radiation? More or less. Okay. So what I'm going to interpret that to mean, so conduction is when heat moves through a material and it actually happens because of the atoms banging into each other, right? Okay. And so that's what happens when you touch hot metal or something and it burns you. That's conduction. Convection is heat being carried by a moving fluid, right? So that's like a cold wind. And then radiation is just hot things. Things with really high temperature will send out heat as electromagnetic radiation. So this happy sun right there, which of these three methods allows us to feel the heat of the sun? Radiation. Okay? Yes? No, it is not. Any kind of material. That's why I said material. So when you get into the water, if the water is still, the heat you feel from it, or the coldness or the heat you feel from it is conduction. And the same for the air. If you walk into a room where the air conditioner has been set at 50 degrees or something, and the air is still, what you're going to feel is conduction pulling heat out of you through the air. But we did say that liquids tend to conduct heat quite well. Solids do. Gases tend to conduct heat poorly compared to both liquids and solids. Okay, second review question. So we talked about two different equations last time, and I really just want to turn that off before we start. Anyway, we talked about two different equations last time. Where would you use each equation? Neighbor it up. Talk to your neighbor. Who thinks their neighbor had a good explanation for this? Yes. Olivia, will you tell us?
The equation on the right is latent, so during phase change you would use that equation, I think.
Yes, so she said the equation on the right here, this is for latent heating or cooling. You use it when there is a phase change. Okay? And so then this one, this is for sensible heating and cooling. We use this when there is no phase change, but the temperature of something changes. So a couple of questions. Let's say you have some ice sitting in a pool of melted water, and it's about half melted. What is the temperature of that ice? 32 degrees Fahrenheit or 0 degrees Celsius. What is the temperature of that water? 32 degrees Fahrenheit or 0 degrees Celsius. And they're both going to stay at that temperature until the melting is done. Another fun, yes?
So what about, for example, if you have like a stove and you throw ice on a skillet, and you have some of the water evaporating and boiling before the ice?
Okay, so when we kind of make an assumption that the heat is going to go in relatively slowly, right? It is possible to just pour it up in all at once, that some stuff will immediately melt and then immediately evaporate. There might be sublimation there, I don't know. So sublimation is when you go straight from a solid to a gas. I don't know if you would have some there, but yeah, in that case I think it's just the heat going in so fast that some of the melted water starts like boiling off at the edge, you know. Fun fact, latent heat is why we sweat, okay? We sweat, water coats us, and then in the sun it evaporates, so it sucks heat out of us in order to evaporate, and we get cooler. By the way, I'm from Mississippi. In Mississippi it doesn't work because the air is too humid. There's too much water in the air, so it just stays on you. So you don't get any cooler, and also you're wet and sticky. Here it works pretty well though. Okay, so industrial settings, we transfer heat in between all these streams. We're always talking about using a heat exchanger. These are two different views of a very common kind of heat exchanger called a shell and tube heat exchanger. And you see all of these little tubes, and what you have is one of your streams. So you have a hot stream and a cold stream, and you're exchanging heat in between them because you want to change the temperature of one of them. And so you send one of them through the inside of these tubes and the other through the outside on the shell. And as you can see in this one, it literally goes out and then turns around and goes back. Does anyone have an idea of why it does that?
So the further that it, like the longer distance it's in contact with the other one, it gives you that convection effect,
Yes.
where it's going to cool or heat more.
Exactly. The longer the two streams are in contact with each other, which means the more surface area there is in between them that's transferring heat, the more of that convection effect there will be transferring the heat. So most heat exchangers try to maximize the surface area, and we'll talk a little bit more about how we figure out just how much area we need in a second. Okay, so heat exchangers have a hot side and a cold side. This is sort of a simple picture. Hot stream coming in, then going out. Cold stream coming in and going out. And then heat transfers from the hot to the cold. And it does it through some wall of some kind of conducting material, usually metal. A lot of metals are good conductors of heat. And so the rate of heat that flows from the hot stream to the cold stream is called the heat duty of the heat exchanger. Okay. All right. So let's say we have an oil refinery. You have an oil stream. You need to heat it to a higher temperature in order to do whatever reaction you want to do with it. So you use a heat exchanger with steam being condensed to water as the heat source. So your cold stream is going to have the oil in it that you want to raise the temperature of. Your hot stream is going to have steam going through that's going to condense to water as it passes. You have complete information about both streams, like so. So I want you to describe two different ways of finding the heat duty. So do two different equations you could use. And I want you to think about it for a second, and then I would like someone who has never answered a question in class to tell us what they think. You know how you think for a little bit.
But it's going to be negative in the hot stream because it's losing water and converting to
So we're talking something, some people are actually doing it, but it's just fine. Okay, so someone who hasn't answered yet, if there's anyone who's willing to give their thoughts, we would all greatly appreciate it. Jacob. Yes, that is exactly right. So what Jacob said is that you could look at either the hot stream or the cold stream. And the hot stream, which is the condensing water. Actually, let's start with the other one first. So the cold stream, which is this oil that's heating up. The heat that flows into this oil is going to be m dot C delta T. And delta T is just going to be 110 minus 35 degrees Fahrenheit. Okay. And then in this stream, on the other hand, it's going to be m dot heat of vaporization. Now, a couple things here. Because this is condensing, so it's going from a gas to a liquid, so energy is leaving the steam. Your heat of vaporization, well, you will actually put in as a negative there, so you would put in m dot times negative 0.74 BTU per pound mass degrees Fahrenheit, and you would end up with some negative number. But when we're talking about the heat duty, we want it always to be positive. So we just take the absolute value and use the positive version. Okay. And these two should be the same. I chose these numbers for them to be the same, so if I didn't make a mistake, they should be. Yes?
Is it okay to work in Fahrenheit? Do you need to convert it to Celsius or?
It is okay to work in Fahrenheit as long as all of your units match. So if you have delta T in Fahrenheit right here, so like delta T is 110 minus 35, 175? No. Okay, someone tell me what that is. Apparently my brain is slow. What? It was 75? Oh, shouldn't have doubted myself. Okay, so this is 75 degrees Fahrenheit. Okay, so then you multiply it by BTU, pound mass, degrees Fahrenheit. And these will cancel out. Right, and then if you then multiply it by pound mass per minute, pound masses, and you will get BTU per minute, which is a perfectly acceptable American units for energy flow rate. If you wanted, you could go from there to horsepower probably. But yes, your units just have to match. Okay. All right, and this is very similar to what you did in your lab with the hand warmer, right? You knew that the heat of fusion that was released by the hand warmer as it went from a liquid to a solid had to equal the sensible heat that raised the temperature of the hand warmer and the water around it. So you could set those equal to each other. Okay. Yes?
On the right side, do we have to multiply by the vaporization temperature as well?
No, you do not.
How does the degrees Fahrenheit on the bottom cancel out?
What actually happens, because actually there's no degrees Fahrenheit in there. That's the actual answer. So, good spotting, eagle eye. And that actually makes sense, because it's heat of vaporization. So all it should be is the heat required to change the phase of this amount of mass. That's what it should be. Okay. So, something that's very important is when you, yes?
You said those were supposed to end up the same, right?
They are supposed to end up the same. If they didn't, it was because I made a typo or something.
Okay. Because I don't think they did.
Okay. All right. I'll fix it before I upload the slides, and you can try again if you want. But yeah, they should be the same. All right. Okay. So something that's really important when we are designing our chemical processes is properly sizing a heat exchanger. We talked about how they have to have all of that surface area touching each other in order to get efficient heat transfer. And so we can use this equation to do that. Write it down, put a box over it, and these are the terms. There's an overall heat transfer coefficient. And when you take heat and mass transfer your junior year, you will learn about all the ways to figure out what that is. For this class, I'll just always tell you. Okay, the heat transfer area. That means all of the area where the hot stream touches the cold stream through that thin metal wall. And then finally, the temperature difference between the hot and cold streams averaged. We'll talk a little bit more about that in a second. And a very common problem is to have to figure out what area you're going to need to do some kind of heating or cooling. Okay, so typical units, just go through this. Watts for the duty, right? So that's energy per time. Meters squared for the area. Kelvin for the temperature. Or we could have the American version. So I just want you to think through for like 10-15 seconds, not long, and try to think what those units of the overall heat transfer coefficient would be. Do you have an idea of what the units would be in SI units? Any thoughts? Okay, it sounds like you unpacked the watts and simplified things. Okay. So it's just, yeah, it's very simple. We multiply by meters squared, we multiply by Kelvin, we get watts out, which is what we want. And something similar with the American units, we multiply by feet squared, we multiply by degrees Fahrenheit, we get BTUs per hour out. So yeah, if you simplify down from here, you will have something with kilograms in it. Okay. But just, I want you to look at those units and feel, I want you to have a feeling that those are the right units that make sense. Okay? So why do we need to average the temperature difference? Alright, so we have a hot stream coming in here and out here, the cold stream coming in here and out here, and what drives the rate of the heat transfer is the difference in the temperature between them. That difference right there. That's going to be changing all across the two streams because both of their temperatures are going to be changing. To maybe make a bit more sense, I've labeled points 1 and 2, where 1 is where the cold stream comes in, and 2 is where the cold stream comes out. And you have some temperature in and out for each of them. Okay. So the cold is going to be heating up, the temperature will be changing that way. The hot will be cooling down, the temperature will be changing that way. And so the temperature difference in between them is also going to be changing all along the way. Does that make sense? Okay, so the temperature difference is changing all along the way, so we need some kind of average temperature difference. And the way we do that is going to be different depending on what type of heat exchanger you're using. I would also strongly encourage you to draw this and label this like I have here to help you keep things straight. I'm going to give you a few more seconds in order to do that. Yes?
Does the heat exchange follow, I guess, a linear plot according to the temperature difference?
Well,
Or
so
does it depend on how big that difference is?
yeah, so it should be linear in most cases, because what it actually is, at any point, the heat flow across that point will be like that. Okay, so that says T hot minus T cold. And so it is this, the heat flow per mass is linearly related to the difference in temperature between, that's not supposed to be something else. Anyway, yes, but we also aren't quite sure how exactly the temperature changes, so I don't know what it would look like if you just graphed the heat flow across there horizontally. But yes, the bigger the temperature difference between the hot and the cold stream at that point, the more flow you get. Okay. Can I get a show of hands if you finished drawing the picture? Okay, alright. So for a simple heat exchanger with just sort of one pass, which is the only kind we're going to be doing in this class, the average temperature we use, the delta T average from that equation, is called delta T log mean. It's the log mean temperature difference. So you can say log mean temperature difference, or you can say delta T log mean, which is slightly faster. And it looks like this. That 1 and that 2 there, those are from here, point 1 and point 2. Okay? Which means And this is why I wanted you to draw that picture. Just keep clear what our point 1 and 2 are, so that everything makes sense. Yes?
Does it matter so much which point in point 1 and point 2 as long as we are consistent?
No, actually. As long as you're consistent, it should be fine. I've labeled them to match up with the picture, which is, I think, pretty common. But if you're consistent, then the signs should just balance out. Oh, I just remember that delta T log mean should be positive in the end. So if you pick your 1 and your 2 in such a way that it ends up negative, just make it positive. Okay. Okay, and remember delta T here is the difference between the hot stream and the cold stream. Okay. All right. So, in the last 15 minutes of class, we're going to do a big example problem. It should be pretty similar to what you do in your lab this week, in many ways. Okay. So we have a chemical process in our plant. It creates a very hot waste stream of whatever. So we want to use a stream of cold water to cool that waste stream before it can be released into the wild. We have the following information about the two streams. Okay. And what I want to, we also know the overall heat transfer coefficient for the heat exchanger. And so I want you to find the exchanger's heat duty, delta T log mean, and the required heat transfer area. So 3 parts. Do them in order. I put them in that order for a reason. You will discover as you go along. I just want you to start. And if you run into any questions, raise your hand. So is which one really small? No, it should be pretty big actually. Okay. Raise your hand if you have the first part, the exchanger's heat duty. Okay, let's get 3 people to say what they got, and if they all got the same, we'll assume it's right. What did you get? 200 kilojoules per second. Okay, someone over here also had it. Okay, who else got 200 kilojoules per second? All right, that is the correct answer. How did we do that? How did you do that? You actually can't use either stream. This one, the cooling stream, doesn't tell you what the flow rate is, so you don't actually have enough information. You had to use this one. What was Delta T? 20 degrees. 20 degrees C. And technically it's negative 20 degrees C, giving us negative 200 kilowatts. But we want duty, which we say is always positive, so we just put positive 200 kilowatts like that. Okay, so, and what did you get for delta T log mean? Oh, you haven't done that part? Raise your hand if you have delta T log mean. Okay, what did you get? You got 16.37. The rest of you who finished, did you get 16.37? Okay, you did not? That's probably why your final answer was wrong. So, okay, so if we draw it here, here's cold in, here's cold out, here's hot in, here's hot out, and we lay it like that in order to try to maximize the difference between the temperatures at every point. And this is 1, and this is 2. So delta T1 would be, hot out minus cold in, which would be 30 degrees C minus 20 degrees C. And then delta T2 should be hot in minus cold out, which should be 50 degrees C minus 25 degrees C. Or 25 degrees C. And so then if you plug them into there, you should get, someone say it again, 16.37, and that is going to be in degrees C. Okay? Cool. And so finally, so we have our heat duty, we have our delta T log mean. So how many people have gone all the way to find the area. Okay? Yeah, I'm gonna give people a little bit more time. We have some time. Catch up. I'll put this here. Again, ask any questions if you don't understand anything so far. Oh, yeah.
I'm gonna make sure that this is in there.
Okay. Now, if you will raise your hand when you think you have the area, I just want to see when most of the class thinks they have it. Okay? All right, keep working.
43.
Yes. Yes. That delta T log mean that was just calculated, that's the delta T average in that equation, the first equation. Okay, in the 3 minutes we have left. Now, how many people have the area? Okay, lots more people. So, what did somebody get? Yes. 43 meters